All right, we're going to finish up Unit 5 today with another application of exponential functions, and we're going to look specifically at exponential growth and decay. And we have an equation here that will describe how things grow at an exponential rate or how they shrink at an exponential rate. And it says here that we have an amount over a period of time, and we get that from an initial amount that is growing or shrinking, and we multiply that by e times kt in the exponent. And what these variables mean is a0 is the original amount. All right, so at is the final amount. A0 is the original amount, or our starting value, what we start with. K is just a rate. I don't know why they use K instead of R, but they're using K to represent our growth or decay rate, and T is represented is representing time. All right, so when we're using this equation, the same for growth and decay, we know it's a growth equation if k is greater than 0 or if k is positive. We know that this function will be representing a decay in value if k is less than 0 or if k is negative. All right, so our first example down here has to do with uninhibited growth of cells. And uninhibited means that our conditions are going to stay the same over a period of time. You're not going to have conditions that will affect the rate, like a change in temperature perhaps, or adding another chemical, or adding air. When you're not adding air, the conditions will stay the same. And here we've got a formula, but it's the same formula that we had up here. We're just changing the variables. Okay, here we want to know the number of cells over a period of time when you start with a specific number and multiply by e to the kt power. All right, so the variables changed, but the process and the meaning behind it did not change. And I'm going to zoom in a little bit here because this is really small. All right, so we're going to use this formula. In the example, it says a colony of bacteria that grows according to the law of uninhibited growth is modeled by a function nt. The number over time equals 100 e to the 0.045t. All right, part A just asks us to determine the initial amount of bacteria. Well, the initial amount of bacteria is the number that's multiplied by the e term. So here it's the coefficient of e, and our initial amount is 100. Part B wants to know the growth rate of the bacteria. If I look at the formula, the growth rate, or K, is 0.045, which is the same thing if I move my decimal over, 4.5%. Okay. Then it asks us, what is the population after 5 days? So I'm going to calculate part C down here. So the population after 5 days, we're going to use the equation, but we're going to plug in 5 for t. So I'm going to start off, I'm finding a number. I start off with 100, and I multiply that by e to the 0.045 times 5. All right, so just on my calculator, clear that out here, I start with 100, and I'm multiplying that by e to the 0.045 times 5. All right, so all of that just calculated in the exponent. And I get 125.232. So n is 125.232. And n is the number, and its says n is measured in grams. So this is grams as my unit. And we should have units with our values that are representing a certain quantity of something. In part D, it's asking how long will it take for the population growth to reach 140 grams. All right, so that's going to be my final number. So 140 equals, and I started with 100 times e to the 0.045, and they're asking us how long will it take us to get from 100 to 140. All right, so first thing I'm going to do, divide by 100. So I have 1.4 equals e to the 0.045 t. And just like when we're working with compound interest and finding t, our t is in our exponent, so I need to do the log of both sides. But because I'm working with e as my base, I'm going to do the natural log of both sides. So I natural log both sides, and remember the property, I can take this 0.045, bring it out in front, 045t, and the ln of e just cancels. So I have ln of 1.4 equals 0.045t, undo the multiplication, divide both sides by 0.045, and t will be, I have ln of 1.4, close the parentheses, divided by 0.045. And I get 7.477. And time in this case is measured in days, so days is my unit. So it takes almost 7.5 days for this 100 grams of bacteria to go to 140 grams. In part E, they're asking us what is the doubling time for the population. So this is just like when we were looking for how long does it take our investment to double. All right, so if I start with a number which was 100, if I'm going to double that, I'm going to get 200. Okay, so in my formula, I go from 102 to 200, and I want to know how long does it take to get there. My rate is still 0.045, and I'm finding t. Now when I divide both sides by 100, I get 2 here, and that makes sense because I want to double my amount. All right, so now I need to get the exponent out. I need to get the variable out of the exponent, so I'm going to natural log both sides. All right, so using the properties, I have ln of 2 is 0.045t, and divide by 0.045, and I get 15.403 days. So I just did ln of 2 divided by 0.045, and that gives me 15.403 days. All right, so next example, same type of problem. I'm looking at bacterial growth, just a different set of circumstances. A colony of bacteria increases according to the law of uninhibited growth. All right, so that equation is n equals our initial amount of n times e to the kt power. Okay, so that's part A. So expressing n as a function of t. Part B, if the number of bacterial doubles in 3 hours, find the function that gives the number of cells in the culture. All right, so in part B, I know if I start off with a number, I want to end up with twice the number. And it tells us it takes 3 years to do that. And what I'm finding here is the rate that this bacteria is growing. All right, so I can divide both sides by n. So I get 2 equals e to the 3k power. And if I log both sides, natural log of 2 equals natural log of e to the 3k, I have 3k equals ln of 2. And if I divide ln of 2 by 3, I get 0.231. Okay, so this is my rate of growth for this situation. So in part C, how long will it take for the size of the colony to triple? All right, so instead of doubling like it did in the first one, I'm going to make it triple. So 3 times the amount is the amount times E. Now, I'm finding how long, so I'm finding the time for this one, but I'm going to use the same rate. So I have 0.231 times t. So my n's will cancel. 3 equals e to the 0.231 t. Now I'm going to natural log both sides, so ln of 3, and I'm going to do a shortcut of not writing all of this out, equals 0.231 t. So I natural log this side, bring this out into the front, and the log and the e cancel out. So now I'm going to divide by 0.231. And my time for this is ln of 3 divided by 0.231 is 4.756. And that would be measured in, how is this measured? Hours. So our time is measured in hours. In part D, it's asking how long will it take for the population to double a second time. Okay, so that means it wants to increase 4 times. So doubling a second time means I'm going to take my first doubling and multiply it by 2. All right, so they do give us a hint here. They want it to increase 4 times. So I'm going to have 4 equals, and I know the n's are going to cancel, e to the 2.231 t. All right, so I'm going to natural log both sides. I'm doing some shortcuts here. I hope you're still following along. It's getting a little redundant. So I'm going to divide by 0.231, and our time on this one is 6 hours. All right, in this next example, we're talking about uninhibited radioactive decay. And notice we have the same formula, and I'm going to give you a hint. Because we're working with decay, our K is going to be negative. Okay, so we're going to have a negative value here. All right, so the situation says that traces of a burning wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. Then it says the half-life of carbon-14, the half-life, and we're going to talk about that here in just a second. The half-life of this is 5,600 years. So approximately, when is the tree cut and burned? All right, so we're going to have to do actually two parts here. Okay, so the first of all, we're going to have to find K. We don't know what the rate of decay is, but I can do that if I think about the half-life. Now, the half-life is the amount of time it takes to get half of the original material. All right, so if I start with N, I want to find out how long it takes to get half of N. All right, so it tells us how long it takes to get half of N, 5,600 years. So if I use that, I will be able to find the rate of decay. So just like we did up above, I have an N on both sides, so I can divide both sides by N. So I have 1/2 equals E to the K times 5,600. And to get that out of the exponent, I'm going to log both sides, natural log, still base E. So I'm going to have log 0.5. I'm going to do this 0.5. And that equals log of this side. The ln and E will cancel. So I have 5,600K. To solve for K, I'm going to have natural log of 0.5. So ln 0.5 divided by 5,600. And for some reason, my calculator is giving me this value in scientific notation. So this is negative 1.2377 times 10 to the negative fourth. So that means I need to move my decimal back 4 spaces, and that would give me 0.0001, and that would be a negative 123. All right, so negative 0.00012, and actually if I round it up, it would have been 124. All right, so 0.000124, and it's negative, and it should be a negative value because it is decay. It's going down rather than increasing. All right, so if I use K here, and I want to find out when approximately 1.67% of the original amount, how long did it take to get to 1.67% of the original amount? So let's think about this. I have 1.67% of my original amount, or 0.0167 of my original amount. Okay, so if I want to find out how long it takes, 0.0167 of my original amount, I'm going to start with my original amount, A0, N0, it's the same thing. So of N times E, my K I know is from down here. So I have times negative 0.000124 times T. Okay, again, so my N's cancel. I have 0.0167 equals E to the negative 0.000124T. All right, so I'm going to natural log both sides. And now I'm going to divide both sides by negative 0.00124. So I'm going to take my natural log of 0.0167 and divide that by my k value, which is negative 0.000124. Oh, I got something that's not working here. Oh, I don't need a, I put a parenthesis here and I don't need that, so I'm just going to delete it. Where's my delete key? All right, so that took care of that. Now I have 33002.79. Since we're talking about a long time ago in years, I'm going to have 33.0, so sorry, 33003. I'm going to round it to the nearest year. 33,003 years. That's a long time ago. All right, so how long ago was the tree cut and burned? 33,000 years ago. All right, so that takes care of that one. All right, next example, Newton's law of cooling. We are not going to do this. Yay, so just cross that out. And the logistic model on the other side, we are also going to cross that one out. All right, so we have just finished what we're learning in Unit 5, and that'll be it. That wraps it up. Thanks.